So I've given you an assignment to read the sample problem that is provided in the second set of slides for the topic distillation. And I have updated, by the way, the slide that is already uploaded in Canvas because there are some errors that I have seen. And then there are, I think, added very important portions in the slides that I think would help you better understand the lesson. So I have added things there on the slide. So your slide now has been updated in case you have already downloaded it, and probably some of you might have printed it already. So the slide was already updated. So I'd like to go through all this. The mole percent of normal hexane in the bottom's liquid for the reboiler in this sample problem is not 98. So I have mistyped it. It should be 90. And the rest of the solution, part of the solutions that are written here are already correct or agrees with what is provided in the problem in terms of the given information. So we also discussed last meeting the first two special cases of rectification. As a review, we talked about the stripping column distillation and the enriching column distillation, in which, of course, we don't have the complete sections of our still, but we only have one of each of the two sections in our still. That is why it's under special cases of rectification. But before we go to each one, anyway, I've just run through as a review what we have discussed last time. Is there any question as to the sample problem here? Is everything that is written in the solution understood, well received, no gray areas, everything is clear? Okay, so your silence means say yes, and I'm happy that you were able to read it and that you understood everything that is written there. Anyway, I won't have placed it there if it's not easy to follow in terms of the provided solution. Okay, so now we will continue with the special cases of rectification, and I think if my memory serves me right, we are on the rectification with direct steam injection. So in here, the reboiler exchanger is not needed anymore. So this is the only type of distillation, a special case that is wherein we don't need the auxiliary equipment, which is the reboiler. Now the next bullet will explain it. So in this case, since we are not needing the reboiler, steam is injected as small bubbles into the liquid in the bottom portion of your column. So there is steam at the bottom portion of the column, and as such, there's no need for us to have a reboiler that will convert the liquid that flows down the column partially into vapor. So there is steam injected at the bottom of the column. So as a consequence of this, your special case of rectification using steam injection requires an extra fraction of the stage, since if we do the process of determining the theoretical number of stages graphical, it will go below the y equal to x line. So that would be shown to you in the next slide. So it will require an extra fraction of the stage. It may not be an entire stage or an additional one stage, but an extra fraction of the stage. Now, it's because your y equal to x line or your stripping section operating line is drawn below the y equal to x line. But this is referring actually to the 45-degree line. I need to accept some of your classmates. Now, it has the advantage of simple construction of the heater in this case. Now, this is the case of our rectification with direct steam injection. So there's no reboiler and steam is injected at the bottom of the column. And as a consequence of that, there is this mention that you will be needing an extra fraction of the stage. If you recall, the graphical approach of determining the theoretical number of stages, the stripping section operating line, this line here below your column, should have been drawn right on the y equal to x line, or the 45-degree line. In this case, it's not drawn right on the projected value of the mole fraction of the bottom's liquid on the 45-degree line, but it's right on the horizontal axis. So in that case, you will be needing an extra fraction of stage, because instead of having it here, now it is right on the x-axis in this sense. So it will not really require one additional stage, but an extra fraction of a stage. So the enriching section operating line is to be still drawn as is, or as the same, or based on the procedure if we were not using steam, or if steam is not directly injected into our steel. As to our stripping section operating line, it will now have a new equation, and that would be W over S, S being the amount of the steam that is being used or injected in your steel, and W is the amount of the bottom's liquid. Now, XM is the mole fraction of the liquid on a particular M stage in your stripping section of your column. And X of W is the mole fraction of the bottom's liquid. In this sense here, this is just given to you as a reference that there is really a change in the manner in which you write the operating line equation for the stripping section. But when we do calculations, we're not really using this equation anymore, because we know that we need to only draw it right on the, either on the horizontal axis using the X of W, or on the projected XW on the 45-degree line, and connect it where the feed line and the enriching section operating line intersects. So we don't need the equation for the stripping section. Actually, it's still same thing even if we're not doing things graphically. So if we're not doing things graphically, we're relying on the use of the table that I shared to you last meeting, and we are not even using there the equation of the stripping section operating line. The equation that we will be needing is the equation of the feed line and the equation of the enriching section operating line. That way we will be able to get the intersection of the two by solving the two equations simultaneously. That is as a review, because we have discussed it also last meeting. So this is the case of rectification using direct steam injected into the steel. So no need for the reboiler. Now, another type of rectification, and this is not covered as well in our, even in the guide for the topic distillation as dictated by our CMO, given to us by CHED, because this will have an extra uh, stream to include in our material balance. But just for your reference, we can also have several side streams or several withdrawal streams in our column. In the case of fractionation, if you can recall the video that I used at the start of the topic of distillation, it's possible to have several side streams in our column, especially if you want to remove products at a certain stage in the column. For that matter. So we will have side stream in here. Just for illustration purposes, John Copley's only used one side stream. Now, this arises when intermediate product or side streams are to be removed from sections of the tower between the distillate and the bottoms. So the side stream may either be in the form of liquid or vapor, which can be removed either above the feed entrance or below, depending on the composition so desired. Now, you can read on this more on section 13-18 in your handbook. Now, this is the illustration, a very simple illustration of a product side stream that John Copley's used to illustrate, wherein you have this additional product stream here, aside from the distillate, where you took a product of stream O, or another side stream product O labeled as O. So in this case, your overall material balance will be, of course, not the simple F equal to D plus W, but this time it will need to account the other side stream or product, and that's the side stream O. If you do a material balance let me go back. If you do a material balance on the upper portion of the column where the side stream was withdrawn, so it's part of your enriching section, and if you're going to make an overall material balance based on this particular portion only, you will have V sub S plus 1 as the stream, the sole stream that is entering, and you have three streams leaving. The L sub S, V by the way is vapor and L is liquid. So L sub S is liquid, distillate is liquid, and O is liquid. It's labeled here as a saturated liquid. So we're drawing off from a column, from this column, a saturated liquid. So it was mentioned that your product could not be limited only to a liquid, but it could also be a vapor. In this example, it's a liquid, a saturated liquid. So the material balance that you're seeing here is just based on the upper portion of the column where the stream was withdrawn. And if you will apply the constant molal overflow based on the liquid streams and on the vapor streams, your Ln is equal to Ls plus O. Your Ln is equal to Ls plus O, because if we will have, for example, this particular plate or stage as our basis, Ln is the stream entering this particular stage, and Ls and O are the streams leaving this particular stage. So Ln is equal to Ls plus O, as you can see here. And V sub n plus 1 automatically, your V sub n plus 1 is the same as V sub s plus 1. Because if it's constant molal overflow, there's no change in the amount of the vapor phases and the liquid phases that leaves a particular stage or tray. And that's the main assumption that we use when we use McCabe-Thiele method of determining specifically the theoretical number of stages and everything that depends on it. Okay, now our equation for the operating line, the additional operating line for a column that has a side stream would be this. Now, if you do things graphical, now you will have four operating lines that will be now appearing in your equilibrium diagram. So you will have your enriching section operating line, the first line that you are seeing here, the operating line for your side stream, this one, your stripping section operating line, and your Q line. Okay, so it will now be requiring another operating line, and of course it will add up to the complexity of having to deal with the problem, but this is discussed in Chan Kupli, so for you to have an idea, this would be possible. Now, can you imagine if we have several side streams, like 3 side streams or 4 side streams in the case of a real fractionating column? That's the reason why when you go to industries, they're not doing it anymore manual, but rather they have softwares that do the computations of the amounts, the compositions of the streams that they are withdrawing at a particular portion or section in the column. Okay, so they don't do it graphical as we do, but it's important that in your stage now, you do understand how those particular softwares were made. So they were made out of these things that you are studying now. Now, there is this thing about what we call a partial condenser and a total condenser. So there has to be a better understanding of what's the difference between a partial condenser that is being used by the column and a total condenser, and how does it affect in determining the number of stages or the theoretical number of stages in your column. As you could see in the illustration class in here on the topic of partial condenser, you see that the first stage here drawn graphically on the equilibrium diagram represents the condenser stage. In this case happens wherein the problem specifies really that you are, or the column is using a partial condenser, not just that you're going to subtract 1 from the theoretical number of stages, but you are to subtract 2, because the first stage that is appearing here in your graphical technique of determining the theoretical number of stages is that of the condenser, but it's not yet part of your column. Okay, but let us define what's a partial condenser and what does it do. There are cases, class, wherein your vapor leaving the top plate of your column has a very low boiling point. And in that case, it would be hard to 100% convert that vapor into liquid or condense everything into liquid. So the vapor in this case, or the product in here, in this case, is vapor. So the product is removed as vapor instead of liquid because of the difficulty of converting all of the vapor from the top plate to liquid. So I have already explained when this scenario happens. So in this case, the liquid condensate is returned to the tower. That part of the vapor was turned into liquid, is returned into the tower as reflux, while those vapors that were not condensed are removed as product vapor. So those that were not condensed were removed as vapor, and those that were condensed are removed as reflux or returned back into the column as liquid. When the time of contact, and this is often the case, class, when the time of contact between the vapor product and the liquid is sufficient, the partial condenser is considered another theoretical stage. Since it is considered as another theoretical stage, so instead of subtracting only one from our theoretical number of stages, we need to subtract two. That way, we are only accounting the number of stages in our steel. We are not taking into consideration the condenser and the reboiler. Now, what about the total condenser? This is always the case, class. When the condenser is able to convert all the vapor leaving the top most plate of your column into liquid, then it's a total condenser. And the condenser supplies the final product, which is now in liquid form, at the same time also the reflux. So concentration of the vapor from the top plate, the reflux, and the product, all three of which are said to be equal. So the vapor leaving the top plate, the reflux liquid returned back into the column, and the distillate liquid have the same mole fractions or concentrations. Now, that's in terms of the total condenser. So I hope you're able to now differentiate between the total condenser and the partial condenser. By the way, class, excuse me. Now we proceed to tray efficiency. Now, we design a column. We know the theoretical number of stages. It's always specified theoretical number of stages. Now, what about tray efficiencies? When the actual column now is constructed, the actual number of stages expected is always more than the theoretical stages accounted, solved for or calculated. So why is that? It's because there's no such thing, there's no equipment for that matter that can perform 100% efficiently based on the design it was created. So if time of contact in this case for distillation and the degree of mixing in a tray or stage is insufficient time and insufficient, or shall I say, non-uniform mixing of the liquid and the vapor, no intimate contact between the vapor and the liquid in each tray, this is not assured, then the streams, that is the liquid and the vapor leaving the stage, are not equilibrated, contrary to the assumption that we are having that the streams leaving a particular stage are equilibrated. That's the same assumption that we started off with the topic of gas absorption and stripping. It's because all these separation processes that we're going to discuss are based on the mere fact that the streams that have been contacted intimately are equilibrated when they leave a particular section or particular tray or a particular stage. So in this case, not so insufficient time, insufficient mixing, so the streams are said to be not equilibrated, contrary to the assumption that they are equilibrated when they leave a particular tray. So then the said tray or stage is not working 100% efficiently. If it's not working 100% efficiently, it follows that your entire still or equipment is not also working 100% efficiently. If it's not working 100% efficiently, the calculated number of theoretical stages will be lesser. The actual that will accomplish the desired separation or recovery in that sense will be higher than the computed theoretical number of stages. So that's why we have this what we call tray or stage efficiency. So we will be requiring more stages than what is computed or calculated for, because we are not, there's no such thing as a stage that is working 100% efficiently. Now, there are several ways of expressing these tray efficiencies, and we have what we call as the E sub O. This is the least fundamental of all means of expressing efficiency of a column. Very simple, so it's least fundamental. When we speak of least fundamental, meaning it's not as accurate compared to the other ways of expressing efficiency. So very simple formula. The number of ideal trays or stages divided by the actual number of trays and stages. So this particular way of determining the efficiency of your column is concerning the entire tower or steel, meaning it's macroscopic. And based on the formula, it's very simple. Why I say very simple, because if you go to the next, and let's say we're just going to compare it with the more free tray efficiency. Now this time, you are not only considering numbers of stages, but rather concentration. So we're now taking into account the mole fraction of the vapor that leaves a particular tray or stage. So it's defined in here what the y sub n, the y sub n plus 1, and the y sub n asterisk represent. So Y sub n represents the average actual concentration of mixed vapor leaving tray n. So Y sub n, the average already, the average of the mole fraction of the vapors that leave a particular tray n. The n plus 1 subscript is for the average actual concentration of mixed vapor entering tray n. So n plus 1 is for entering streams, averaged, and n is for leaving streams, vapor that is, because we are using y, and also average. The y sub n asterisk is the concentration of the vapor in equilibrium with the liquid leaving a particular tray. So what is the concentration of the vapor that is in equilibrium with the concentration of the liquid that on the average that is leaving a particular tray through the downcomer? So the liquid is actually guided by the downcomer in flowing down the column or steel. So this is our formula. This formula gives you a much more accurate way of expressing the efficiency of your column. And oftentimes, this is the efficiency that is given in problems. Given, for example, the Morphy tray efficiency, how will you account for the actual number of stages in the actual steel that has to be constructed based on the calculated theoretical? So most of the problem, if you have read already, is giving this Morphy tray efficiency, not the overall tray efficiency. Most of the time, it will just simply ask you what is the overall tray efficiency, but it will not give you the overall tray efficiency. That way you can come up with the actual number of trays. So that's the Morphy tray efficiency. If this one is now considering efficiency based on concentrations on a particular tray as average, and this is more accurate than the overall tray efficiency. This one is even more accurate, okay? More accurate than the E sub m, because this one accounts for the concentration on a particular point on a particular tray. So not just that we are looking into the average concentrations of the vapor leaving and entering a particular tray, but rather we're looking into a particular point on the tray and what is the concentration of the vapor living and entering that particular point on a particular tray. And that is why John Couples made it specific to write it or distinguishes it from the one that is used in more free efficiency with the use of the primes here. The only thing that was intact is the y sub n asterisk. The rest have the primes already. So y prime sub n is the concentration of the vapor leaving a specific point on tray n. So the y prime sub n plus 1 must be the concentration of the vapor entering the same point on tray n. And y sub n asterisk is the concentration of the vapor in equilibrium with the liquid living at the same point that we're talking about in here in the y prime sub n and the y prime sub n plus 1. So take note that if the first one is accurate, the more free efficiency, this is even more accurate than the more free efficiency. Okay, so we have three ways of expressing the efficiency of our column. And of the three, of course, this is the most, I'm referring to the more free point efficiency. This is the most accurate. But this is least used, seldom used. We use often or we encounter most of the time the more free tray efficiency. Now, on a pictorial representation of the y's and the y prime, so this is your y sub n, it's average. This is your y sub n plus 1 average. So it enters a particular tray n. This one leaves a particular tray n. So all of this is average when we speak of more free efficiency. But when we speak of more free point efficiency or simply point efficiency, we're dealing with a particular point on a particular tray. So then it must be the most accurate way of expressing efficiency of your column. Now, how do we go about, or before that, there are generalizations summarized by John Couples as to how does yn or y sub n prime compares with y sub n asterisk. Since your y sub n asterisk is already the concentration of the vapor in equilibrium with the liquid leaving a particular tray or a particular point on a tray, then the value of y sub n prime could not be greater than it because this one is already equilibrium value, meaning this is the highest concentration already. Whereas the y sub n prime, the concentration of the vapor leaving a particular point on a tray is not yet equilibrated. This one is equilibrated. So this one is higher than this. And that has to be always remembered because local efficiencies cannot be more than 100%. Cannot be more than 100%. When you speak of local efficiencies class, just like when you speak local news, local, anything local, meaning it's more specific on a particular location. Now, when we compare small diameter towers to big towers, meaning that, of course, towers that have big diameters, in the case of small diameter towers, the vapor flow sufficiently agitate the liquid because it's small, so that it is uniform on the tray, which makes the concentration of the liquid leaving the tray the same as that on the tray, making the point efficiency equal to the more free efficiency. Bottom line of this particular statement here or bullet is that in the case of small diameter towers, we can say that the difference between the point efficiency and the more free efficiency is negligible. They are more or less the same. Okay, it's explained anyhow. For larger diameter towers, we expect that since the more free point efficiency is much more accurate than the more free efficiency, then we say that the more free efficiency would be higher. Naturally, it would be higher because it's not as accurate as the more free point efficiency. This is for large diameter towers. Now, there is this equation that relates the more free efficiency to the least fundamental way of expressing efficiency, and that's the overall tray efficiency. And it will be needing the slope of the equilibrium line if it's a constant, and the slope of the operating line. Okay, the slope of the operating line is assumed to be a constant most of the time, and the slope of the equilibrium line is not, of course, constant at all times. So meaning, in this case, the formula will only hold true if we have an equilibrium line. In most cases, we have an equilibrium curve, so this formula will not be anymore applicable because this one is only for equilibrium lines. Okay, now the thing with using efficiencies, or how do you, or where do you often encounter this Morphy efficiency, and how is it being introduced in the problem, or how will be a problem created out of this concept? Now, if you use the Morphy efficiency that is given in the problem, the usual way of tackling the problem or solving for what is required, most of the time it has something to do with the actual number of stages, is done graphically. So I will explain it in the shortest way possible, in the simplest way possible in here. So what you have is your, for example, this is your equilibrium curve. This is your 45-degree line. This is your enriching section operating line. This is your feed line, and this is your stripping section operating line. Now, I'd like you to look closely at it, let's say for a minute or so. Probably some of you may have an idea on how is the Morphy efficiency, so I'm saying it's the Morphy efficiency, being used in determining the actual number of stages graphically, looking at the graphical illustration. Or probably some of you have read already the assigned pages, so you will have an idea on how is this to be answered. So how do you think will the actual number of stages be accounted for using the Morphy tray efficiency? By looking at the diagram that is shown to you now. It seems like you have an equilibrium curve here. This is your original equilibrium curve, and there seems to be a new equilibrium curve drawn here. So I'm giving you a clue. You have drawn a new equilibrium curve. The rest of the procedures in plotting the operating lines are the same. So if we use Morphy tray efficiency in determining the actual number of stages, anybody here who happen to have read this part of the assignment already, or of the book that explains how the Morphy efficiency could be used in determining the actual number of stages, because in the formula you don't see actual number of stages there. All you get to see are just mole fractions of the vapor because it's all Y's. Anyone? What do you think? You have here the Y sub n plus 1, you have the Y sub n, and you have the Y sub n asterisk, and you have A, B, C. What does these points here, what are the significance, or what is the significance of the points A, B, C in here? Anybody? Okay, so no one have read in advance. Okay, this is what you do. So you know already how to draw the operating lines. It's a given. And this is your original equilibrium curve. You have to draw straight lines randomly. So let's say you draw one straight line here. The more straight lines that you make, the better. So I have another straight line here, another straight line here. Take note, I'm starting from the curve down to the operating line. In the upper part, of course, down to the enriching section operating line. In here, on the stripping section operating line. So I have, as I said, the more vertical lines you have, the better. Okay? You have drawn already vertical lines. Now using the more free tray efficiency that is given in the problem, you will measure the lengths of these lines that you have drawn. Measure, like let's say this is 1 centimeter, this is 1.2 centimeter, 1.7, and so on and so forth. Now using your more free efficiency, let's say for example, for a more free efficiency of 0.7, the distance of AB is, let's say, 0.70% of the distance AC. I gave a more free efficiency of 0.7. That's very low, but just for illustration purposes. So you have a more free efficiency provided by the problem, which is 0.7. How will you now use that 0.7 in making this curve, this new curve that you have? What you will do is determine the length of the lines that you have here and multiply that by 0.7. That 0.7 is the value or the length of the line from the operating line to that curve which you will draw. That curve that you will draw. So you, let's say, like I'm saying, AB over AC is 0.7. This distance to this point is 0.7 of this distance to this distance. So out of these lines that you will have that you have drawn vertically, you will have points. So I have points here. Now I have this point here. I have this point here. This one, this, and this. The distance from the operating line to that point on this vertical line is 70% of the entire length of this line, because as an example, I gave a more free efficiency of 0.7. What you will do next is connect all these lines. So starting here, you connect all the points that you have on your vertical lines. That way you will have a new curve. This new curve, since it's nearer your operating lines, will give you a number of stages that is more than the number of stages if you use this original curve. Now, that's how you use the more free tray efficiency in determining the actual number of stages. So this, when you construct this, when my students construct this before, they need not have the same lines, because your lines will be randomly selected by you, depending on the accuracy of the curve that you want to draw. The lesser the number of lines that you have placed in here, the crude is your curve. So your curve will be very crude if you only have very few vertical lines. But it would be more accurate if you have a lot of vertical lines here, meaning points that are more adjacent, giving you a much more better freehand drawing of your new curve. Now, when you draw your curve, it's freehand. So you do it freehand. You don't connect like as if you're just connecting the dots. No, it's just like drawing the best fit curve or the best fit line. So you draw it freehand. Then based on the curve that you have drawn, you make stages, or you draw stages starting from XD down to XW. Now again, notice this is something that I'd like to zero in, this one. This particular stage here, if you notice, did not end on the curve that you have drawn, on the new curve you have drawn, but rather it ended here on the original curve. What do you think is the reason behind that it went beyond the curve that you have drawn? Why does this stage has to be right on the original curve for the system that is provided to you? This last step only. Why is that? Do anybody have a guess? Why do we need to draw this step here right on the original curve but not on the curve that you have drawn yourselves based on the Morphy efficiency?
Lapaw, nasa ni sa reboiler, miss?
Because, so the answer to my question is after right here, because it has something to do with the step here representing the reboiler. Remember, the reboiler is not part of your column. Hindi siya part sa column mo. So, hindi siya mag-untat dira sa curve nga gindraw mo. Kaining curve nga gindraw mo, iya na sang column. So since the reboiler is not part of your column, the way you draw the last step here, you would know if it's the last step because you're about to go beyond or and write on X of W. This is your reboiler step. So it has to be drawn on the curve, the original curve of your system, whatever that system may be. Do you get it? So that's it. When you draw it or when you do these things graphically, if you will be given this, it has to be on the curve, not on your curve. Your curve because you're the one who draw it freehand. Do you get the explanation on using the Morphy efficiency and determining the actual number of stages? Do you have any question and as to how is it to be used?
Hello, miss. Good
Yeah,
afternoon.
yes.
Si Joshua, miss.
Sige, Josh.
If partial condenser, miss, amo man na Japan, di ba, miss? Hindi na siya, miss,
Ang
maglapaw, yeah, miss.
Okay. Kung partial condenser siya, 'di ba ang partial condenser ang first mo nga step sa babaw ano ng iyas ang condenser, it's the same thing with total condenser. But the thing is, kung partial condenser, gina-consider tanga ang una, tanga step nga gin-draw ng iyas ang partial condenser. Kung total condenser, ini siya iya ginisang column. Ini siya iya ginisang column. Pero kung ang problem Diyos naghambal nga partial condenser siya, then iya ginisa iya sang partial condenser. And as to the question, ti Miss diin siya namon i-draw. That's a very good question. So if it's specific in the problem that you are provided with a partial condenser, when you draw, it's just like this one. You go beyond the curve that you have drawn, just dito ka, nan, and then manaog ka. Then diri ka na dayon niya sa dason. But you need to subtract this because this is your partial condenser. So instead of subtracting 1, you need to subtract 2. But the problem have to specify it. Hindi ta mag-assume ko ang problem wala siya nagambal, then it's a total condenser.
Okay, miss. Thank you.
Sige. Question. So, importante na intindihan ang pag-draw sang line sa. So, you measure the length of the line that you have drawn from the operating line to the curve or from the curve to the operating line. It's the same length anyhow. But what is important is that from the operating line to that point where your new curve should be drawn, that should be your Morphy efficiency. Like AB to AC is your Morphy efficiency. So you're the one who's getting the value of this. So what you do, you measure all the lengths of this line and multiply it by the Morphy efficiency. Then measure right from the right on your operating line up until that particular value that you took from the product of Morphy efficiency and the length of your line. Then you connect all those points. That would be your new equilibrium curve. There's no problem the using Morphy efficiency that's solving it without using the graphical technique class. It has to be really drawn this way. If you are to use the Morphy efficiency in determining the actual number of stages. Because based on the formula, we don't have a formula for Morphy efficiency that is based on actual number of stages. But rather what we have are concentrations. Okay, this one you can read. So for those who would like to read more on this, you can read this in Gian Kuplis. This is clearly, and this one I think is from Gian Kuplis. This is clearly also explained by Gian Kuplis with a specific example. If there's no example anyway, the illustration is very simple to understand on how to determine the points that you need to connect so that you will have your curve, the curve that you will draw freehand. Okay, now we will proceed if there aren't any questions anymore. Okay, so we will proceed with the next part of the slide. Okay, I need to erase. Now, when we speak of efficiency and when we speak of the height of the column, it's the same as gas absorption. You remember gas absorption, we have N theoretical number of stages times HETP is the height of your column if it's a packing column. So it's the same thing with distilling tower. We can have packing materials inside our column. We can have trays with perforations. It could be bubble trays or sieve trays. It's just like gas absorption. So it's the same thing with distillation. So when we speak here of HETP as a review, it's the height of the packed column necessary to give a separation that is said to be just like equal to one theoretical plate or stage. Height equivalent to a theoretical plate. So that's P or stage. The height of the entire column, it follows, then would be the height of a particular packing material equivalent to a plate times the theoretical number of stages. Then that would be the height of the entire column of all or of the packing material that you will be using for your column. Now, we can have also H, if we don't want to use this particular formula having the HETP, we can also have the Hognog formula, just like in gas absorption. The O that you see in the subscript, I hope you haven't forgotten it yet. The O that you see in the subscript mainly specifies that it's the overall mass transfer unit that was used as a basis. If it's not the O, or if it does not contain the O, then it's just the mass transfer unit, but not the overall mass transfer unit. It's just a case of using formulas that are, shall I say, dimensionally the same. So if you will multiply a hog, it would be to a nog. You will not multiply a hog to an ng only. So they should be paired with each other. So H here is the overall height of the transfer unit, and NOG is the number of transfer unit. So if you multiply the two, that will give you the height of your column. If you'd like to get the HETP equivalent using the hog, then you will be needing the slope of the equilibrium line and the slope of the operating line. Now, however, class, again, since this is the slope of the equilibrium line, if you have a curve, you cannot use this formula anymore. And this one is only applicable when your equilibrium and operating lines are said to be parallel. No? Ini siya ang conversion formula of the hog to the HETP. How do we determine the HETP for a tray tower? HETP. Let's say you're given the spacing of your tray tower. What is its equivalent in terms of a packing material? Okay, so this is it. This particular formula is empirically determined, so the values are applicable to the tower diameters here, and or the range of the tower diameter in the case of the last one. So T is the tray spacing. You have to know though the overall tray efficiency, theoretical over actual, to get the HETP. So if your tower diameter is 0.5, this tray spacing is 0.3. If it's 1 meter, it's 0.6. If it's greater than 4 meters, then that would be 0.8. Oftentimes, there's no problem because if we are to use this empirical equation, empirical formula, John Couples, this is provided by John Couples, specifies the diameter within the range that is applicable to the given formula that he also provided. So mahambagi na siya nga 0.5 or mahambagi na siya nga 1 meter or mahambagi na siya 5 meters or something like that. So you'd be able to know the tray spacing that you will appropriately place here on the formula. Now, if you have John Couples and if you don't have John Couples, there are available PDF copies online. These are the different formulas that you'll be using for HETP for a random pack tower. And this one is for an overall efficiency for sieve and valve trays. And this one is for absorption towers. So this one is not applicable for a topic now, but it's included in that particular page. This one is for vacuum service, and this one is for structured packing, meaning if you have a structured packing material and you want to determine the HETP, how would you determine it? It should be this equation that will give you that formula. So I did not anymore write it here. You have just to locate it in Janku, please, in this page. By the way, this is the Philippine edition, the one that is colored black. So you will have these equations there. So take note that we have a different formula for structured packing and for random packings. And this one accounts for the overall efficiency for a sieve or valve tray. And this one is for a vacuum service. After our discussion, review these formulas. If you are a little bit confused on which one to use, just message me so I can clarify things. That is, if it's still not clear to you as to what particular formula to use. Now, we are now on the last part, and actually, even if this is the last part, oftentimes in my experience before, this is the part wherein I would hurriedly explain everything because I ran out of time. So I am now actually happy because I placed distillation on top and the rest of the topics below, because in terms of importance, I really find this particular topic important compared to the others, and in terms of its probability of coming out of the board exam. The last part of this section is in determining the reboiler and condenser duties. What's a reboiler duty? So when we speak of duty, what's the objective of the reboiler? So it has to provide the energy necessary, that way a portion of the liquid that is flowing down your column is returned back into the column in the form of vapor. Otherwise, there won't be any vapor that will flow countercurrent to the liquid that is flowing down or that is going down. That's the objective, that's the purpose of your reboiler. So when we speak of the reboiler duty, how much energy will your reboiler provide? That way, it will be able to turn the liquid to vapor. But not all is to be converted to vapor, because we really have to have a bottoms liquid, or there's no need for all of the liquid that is flowing down the column to be converted to vapor. So only a portion of that. So reboiler duty, that is its duty. When we speak of condenser duty, how much energy will the cooling water of your condenser remove? It will need to remove a certain amount of energy from the vapor, leaving the top plate. That way, that vapor is all, if it's a total condenser, is all converted to liquid. So that is its duty. So when we speak of reboiler and condenser duties, which I will be discussing in a few minutes, we speak of the amount of energies that are to be supplied and withdrawn respectively for the reboiler and the condenser. That way, they are able to perform the function that they are to perform in our column as auxiliary equipments. Okay? The discussion of the reboiler and the condenser duties can be found in John Copley's. McCabe does not in detail discuss the condenser and the reboiler duties. Now, what you see here is it's very obvious. It's the enriching section of our column. You don't see any feed because the feed is in the stripping section. So what you see here is the condenser, the reflux, the vapor leaving the top plate, and the distillate. And we have this tray N, we have this tray N plus 1, and the corresponding streams labeled based on this labeling of the plates or stage in your um, enriching section. Now, if we make an overall material balance on this section only of your column, based on the streams that you are seeing and on tray N in here, we have V sub N plus 1. It's entering this tray N is equal to, so there are only two streams leaving this section, the Ln in here and the D. the Ln and the D. So this is your overall material balance for your enriching section. The component balance, of course, is patterned from this. So all you have to do is multiply it appropriately with the mole fraction. So if it's vapor, it has to be Y. If it's liquid, it has to be X. So they were labeled in the same way we labeled the stream. So we have material balance and we have component balance. The next is we do energy balance. So when we do energy balance from thermodynamics, when you speak of energy, automatically enthalpy plays a very important role. So when we make an enthalpy balance on the entire enriching section, now you need to add up the QC because you have energy for this particular stream, the Ln. You have energy for this particular stream, the V sub n plus 1. You have energy for this particular what did I say, Tray? Ln for this particular stream, this one V sub n for this particular stream, the D, it has also energy, and of course the Q sub C. This is energy that has to be removed from the vapor, that way it can be condensed to liquid. So it's living, living, living. We only have one stream in which energy is to be a plus sign. The rest are all negatives. So when we write the energy balance with the enthalpies, it would be something like this. So Ln, the D, and the QC, they are all energies, living or withdrawn energies, and this is energies added to. So this is plus, all of these are minus. Now, but when we make an enthalpy balance around your condenser only, if it's just on the condenser, this would be the enthalpy balance or energy balance just on your condenser. So we go to the condenser, go back to the condenser. In your condenser, there are three streams. The V1, you see this V1, the L, and the D. Okay, so this is living, this is living, this is living. That's the only thing that is positive. The rest are all negative when we speak of the condenser only, not the enriching section. We're just talking about the condenser. So when we do the energy balance on the condenser, you will have this. These two are negative because they're supposed to be together with the QC. This is the only thing that is positive. So it's written there that way. What do you think is the purpose? We can substitute for the QC that you have here on the third term on the right side of the equation, all of this. This QC here will be this. So your operating line equation is just a review in here because I have written the component balance equation here. So the operating line equation, just like what we did with the enriching section operating line and the stripping section operating line, we isolate the Y sub n plus 1 here, or the Y sub m plus 1 in the case of stripping. So you divide by the V sub n plus 1. So this is your operating line. The final working equation, this is just but a review of what's written here, by the way, here. The final energy balance or the final working equation for the energy balance in your enriching section would be this. We copy this one. We change the Ln based on the overall material balance we have here. So it's V sub n plus 1 minus D. So it's the thing that you're seeing in here. We multiply it with H sub n. And as I have said, this DHD is copied, but however, this Q sub C, the condenser duty, is this. So if you place it in here, this one and this one cancels each other, giving you this one. This is the final working equation for the energy balance in your enriching section. However, if you would just be asked by the problem, what is the condenser duty? And if all of these are readily available, anyway, enthalpies of the distillate is based on the mole fraction of the component in the distillate. I'll be showing to you the enthalpy diagram and next meeting if we'll have not enough time now. So this would be your condenser duty, an equation that will solve for a condenser duty. The energy balance for the enriching section would be this one, taking into account already the condenser duty. if we did energy balance on the upper part or section of the column, we do also energy balance on the lower part of the column. And this time you already have the appearance of the feed because it's in the stripping section. And we labeled the particular stage here as M because we used N for the upper portion. And if we do material balance here, we have W, this W is equal to V sub M plus 1. So this one is living plus your V sub M plus 1 rather plus your W living and living is equal to the only stream that is entering this section here. So take note, we did not account for the feed. So you have that as LM. When you write down the component balance, it's patterned on your material balance. So whatever you have written here, you just multiply it by the mole fraction. The operating lines are determined just like what we did with the enriching section. Now, your energy balance, this is your final working equation. Sorry, class. Wait. Why is it that I don't see a final working equation here? This is your final working equation. This should be class here. Na interchange sila. This is the operating line taken from the division of this equation by LM. So that would be your operating line. Rather, transferring the W, XW in here, dividing it by V sub M plus 1, that should give you the operating line equation, this one. Okay, this should be here. And this one is the energy balance around your reboiler. Around your reboiler. So this is the energy balance in your reboiler. Where is that reboiler? Let me go back. This is your reboiler. So the energy balance on your reboiler will account for the energy content of W, the energy content of this particular V sub N plus 1, and the energy content of L sub N, because this one is L. What is introduced into your reboiler is L sub N. Now, this is your final working equation for your energy balance around your reboiler, taking into account already the equation for the material balance. Take note, class, that L sub M was already replaced by V sub M plus 1 plus W in here, your L sub M, HM. V sub M plus 1 multiplied to enthalpy, this is your LM, HM, and this is plus QR minus WH sub W. This is the final equation for your energy balance in your stripping section. Q sub R is your reboiler. The only way that you can determine Q sub R is for you to know Q sub C. If the problem gives you Q sub R, you can also solve Q sub C provided that you know the streams, the W, the feed, and the distillate. Now, these three can be solved by pure material balance around your column. No need for energies for that matter. You know how to do this. It's very simple. The enthalpies will be taken from an enthalpy diagram. I will have it sent in Canvas. What's an enthalpy diagram, where you're going to use the mole fraction of a particular component that is to be transferred from the feed to the distillate, or the least boiling component. Amo na siyang ginabasihan magkuha sang HW, HF, kag HD. The component that is most volatile, or the one that has the least boiling point. That's what I mean. So you need an enthalpy diagram for this. In getting this, you need the mole fraction. So everything is just a substitution to this, as long as you know the mole fractions of these streams. And you know this by material balance. So this equation relates the Q sub R and the Q sub C. One can be known if one is readily available. So I can solve for QR if I have QC, or vice versa. I can solve for QC if I have QR. This is your reboiler and condenser duties. Now, in the last part of this slide, I have indicated a sample problem in John Copley's, which you can read and easily understand, because I know John Copley's is really easy to follow as to the application of the formula that I have just shared here with you. So those formulas, actually, the very important ones is this. I'd like you to remember this for the QC. The final working equation for the energy balance in the enriching section, the formula for the QR in terms of QC, and the final energy balance equation for the stripping section of your column. So 4 energy equations, balance equations in your distilling column. There's one particular problem in John Copley's that helps you understand how this particular formula works and how you're going to uh, use it. Okay? Read that sample problem, and I will give another sample problem on Monday regarding this one. That way you will have 2 sample problems on this particular topic. So that's in terms of the reboiler duty and the condenser duty. Now, the last part here is determining the steam requirement or the heating requirement. For the reboiler to function as it is designed to function, it has to have steam. How much steam will be able to turn the vapor, or rather the liquid, into vapor? This one now is available in your handbook. This formula is available in your handbook, and this one this time is available in McCabe. I'm sure probably 1 or 2 of your unit ops teacher have also mentioned that ang representation ni McCabe kag iya ni Paris is same. It's John Copley's that has a different representation. If you see a formula in McCabe, more likely you see that formula in Paris. If that particular formula is from John Copley's, Paris may have an equivalent, but it's different in the way the streams are labeled, or the way streams are labeled, gidya. Because McCabe and John Copley's are totally different in the way they represent even the streams. So as for heating requirements, the steam requirement, you have this as the formula. If you have read the sample problem that I placed you to read in Canvas, I think it's sample problem 21.1, the first sample problem in McCabe. In one problem, everything is discussed already, from the number of stages to material balance to these heating requirements and cooling requirements in just one problem. But it's of course a very long problem, but it's easy to follow as long as, of course, you write down the steps on how you go about determining the unknowns. So in here, this is the formula in determining the steam flow rate. So MS dot, meaning it's the mass flow rate of the steam. So you have latent heat of the steam, molar latent heat of the mixture for lambda, and V bar as the vapor rate from the reboiler. This is equivalent to the V sub n plus 1 representation of John Copley's. If you've read John Copley's, the V bar is V sub n plus 1 in John Copley's. So this is V bar in McCabe. This one is McCabe's representation. So the reason why I'm telling you, kay lain ang representation ni McCabe kay John Copley's. For cooling requirements, also in one problem, you have this. How much water does your condenser need to convert your vapor to liquid given the temperature of that particular cooling water? So this is the formula. We have the B lambda divided by T sub 2 minus T sub 1, the CP of the water that is used. Most of the time, class, para simple, wala na siya naton, gina-average. There is this problem in heat transfer that when we speak of condenser, the CP that goes with the difference in temperature is based on the average of these two temperature. But the difference of the answer, whether you base the CP on the average of these two or the CP based on just one temperature, and that is the room temperature, is very negligible. So for things to be a lot simpler, just base it on the a CP of water, the standard CP of water, and then multiply it with the difference in temperature. If you want it more accurate and if you have the time, you can really get the CP of water if you want, based on the average of these two values. Okay, temperature and the average of these two values. So you add and divide by 2 and then get from the appropriate property table for water the CP at that particular average temperature. That would be the CP that you place here. If the problem does not specify, you can just readily use the standard CP for water. Okay, this is the cooling requirement for your condenser. The last part here is just an assignment, which I also wrote in Canvas for you to read. This one, there were three actually. This one specifically discusses the use of the formula for the condenser and the reboiler duties, which I discussed, coming from John Couples. This one specifically uses the formula that I have mentioned regarding heating requirements and cooling requirements based on McCabe. So you have two books here to use. That way you can appreciate the application of the formulas that I just have shared with you. So you have to read this. On Monday, I will give you examples different than the one that you are reading now. That way you can more or less have an idea on what I'm talking about on Monday when I discuss to you sample problems related to what I have discussed this afternoon. Okay? Do you have any questions?
Hello, Doc Ali.
Yes.
Joshua, Doc. Hindi,
Yes.
Doc, i-clarify ko na lang, Doc, about ni Tani. So, sa first, bala, Doc, ha, ang calculating for the
Ah.
actual number of stages, bala, Doc.
Mm-hmm.
Kay, i-clarify ko lang, Doc, if mag-determine, bala, Doc, sa intersection between the feed line and the equilibrium curve, Doc, graphing lang gina, Doc, ang pwede, Doc. If hindi given ang equation of the equilibrium curve,
Dali lang, dali lang. Ang intersection sang ano namin mo, ang intersection sang feed
sang
line
feed line, bala, Doc,
kag
and the equilibrium curve to solve kag ang equilibrium curves to solve for the
okay,
minimum
okay.
reflux ratio bala Doc.
Okay, sige, sige. So, hindi siya clear amo ni. Actually, mag-determine kita sang pinch point. When we determine the pinch point, it's the intersection or of your feed line to the equilibrium curve, right? But we don't have an
Yes, Doc.
equation. We're not provided with the equation of the curve because anyway, it's a curve, it's not a line. It's difficult to find the intersection of the curve with a line. So to simplify things, when you look at the graphical technique of determining the pinch point coordinates, isn't it that the intersection of the feed line and the equilibrium curve is where your enriching section operating line is also connected to during the determination of the number of state of the minimum reflux ratio. You recall? Hindi bala kung diin siya nag-intersect si feed line, yung buhon ko na lang ha, sa equilibrium curve ng digto tama na gina-connect si enriching section operating line halin sa XD. Kasugat anay na to sila nga tatlo.
Yes, Doc.
So kay wala kita gina-providean sang equation sang equilibrium curve. Ang aton lang magamit is ang equation sang enriching section operating line nga ma-set up kaya based on reflux ratio. Kag ang equation man sang feed line nga ma-set up taman based on reflux ratio and the value of the Q, then we have two lines. Actually, ang ginapangita tanga intersection ni equilibrium curve kag ni feed line, ginpangita ta paagi sa pagpangita sa intersection ni feed line kag enriching section operating line because these three will meet at one point for the minimum reflux ratio where we determine the pinch point coordinates. Did you get it?
So bali Doc, malain pag Doc ang equation for the enriching section at the pinch point, Doc.
Hindi. Ang enriching section operating line mo nga nga equation niya amo gina siya, wala gina sa nag-change lang. Makadto na lang ko sa ano ha, kadto ko specifically sa PowerPoint para clear. I-share ko na lang dayan ang slide, dali lang din. Ay kay na confuse ka mo. Okay, ari siya. Ha? Okay, I will stop share. Share new screen. Relation part 1. Do you see my screen for the operating line equation of the enriching section?
Yes, Doc.
What you need here is the reflux ratio and the distillate. Okay, the mole fraction of the distillate. This is your enriching section operating line. The only unknown that you will have here, Josh, is the x and the y. The rest are all known. So, may equation ka na sang y in terms of x. Right? Now, next is you will use the equation for the Q line. Oh, ay, liguro yan ni Q line. Sorry. This is the equation of the Q line, which I said is dependent on the Q and the feed line, the feed mole fraction. So your only unknown here is just x and y. So you will get the intersection of this equation and the equation for the enriching section operating line. That would be your pinch point already, Josh. Nga aman, gasunod malang na iya si enriching section operating line sang intersection ni feed line kag curve mo. So meaning ang tatlo makit-anay gid sa isa ka point. Kay tungod wala kita sa equations ng equilibrium curve, what we use is just the equation of the enriching section operating line and that of the feed line. That would give us the x and y, the x prime and the y prime for our pinch point. Not that nga may different kapag yung equation nga gamiton nga enriching section operating line just for you to be able to find the x prime and the y prime. Did I make it clear?
Hindi ko gets, Doc. Kay bali, Doc, may ang operating line bala, Doc, sa first, bala, Doc, how ang enriching section gamit sa, di ba, Doc, with Q line in the middle. Hindi siya, Doc, gamit with the Q line at the equilibrium. Kung
Eh,
pinch pag bala, Doc, how?
kung pinch point, ang pinch point nagakit-anay nada sila nga tatlo, dali lang. Minimum number of stages are there. Minimum reflux for the pinch point. Hara, Joshua, amo na ginanamin ko.
Ay, okay, Doc. Pero ang for me, same yun sa, Doc, sa for, and ado bala, Doc, ang solve kami bala, Doc, nga sa tunga sa isang Q line gamit bala, Doc, ang enriching operating line bala, Doc, how kung mag-solve for theoretical number of stages.
Sa theoretical number of stages, mag-solve sa theoretical number of stages.
O, kay di ba, Doc, giduga saka saya bala, Doc, how
Di wala man taga-solve sa theoretical number of stages, Josh. Based ang aton theoretical number of stages based sa curve nga share ko sa inyo, why taga-solve? Why ta siya gina-solve? Ari siya Wait lang. New share. Do you see the graph determination of n? Or I was not able to share it yet.
yes, Doc, Doc.
So why taga-solve, Josh? Gina-solve ta ni siya ho based sa pinch point. Gina-solve ta ni siya based sa pinch point nga amo tong ako nga procedure nga gin explain a while ago. Together with this, you'll be able to get this ratio. When you get this ratio, you have the option. Ang N minimum, you can determine graphically because it's very simple, or you solve it using Finsky based on the sample problem we just read. And if you know this using the ratio that you got here, you'll be able to get the N. Wala tagid siya ginasolve si theoretical number of stages. Ginabasa ta siya sa curve.
Yes, Doc. Gali, ang kina-confuse ko lang bala, Doc, ha, kay kung ang enriching section, bala, Doc, na equation,
Mm.
kay kung ano siya bala sa intersection, niya bala, Doc, sa Q line,
Mm.
na, lang siya bala, Doc, sa tunga, Doc, hindi siya bala, Doc, connect sa
Kaya ang imo,
equilibrium.
kaya ang imo na daya goal ya Joshua, hindi man niya nga magkuha ka sa theoretical number of stages ang pagkuha mo sa intersection. Ang goal mo daya kay pangitao mo si pinch point para makuha mo si R sub n. You're
Ang,
not
ano, yes, Doc.
you're not determining the theoretical number of stages, but rather you are determining the pinch point. That way you can get the R sub m. That way you can use this to get the N. Kay basi balang ara sa inyo ulo nga kinahanglan ma-intersect siya sa tunga-tunga nga pareho sa pangplata nga ini nga sa graphical, hindi man na siya amo.
Okay, Doc. So,
Dali
bali,
lang. Dali lang. Dali lang gida ahay. Kaya ang inyo nga sa mind yung amo niyo. Nga amo ning sulbo nyo? Is
ay,
this the
Doc,
one you're telling me that this is the point that you want because anyway you're determining the theoretical here?
hindi, Doc, bali, Doc, ang ginamin ko bala, Doc, ang equation of the enriching section is this one, Doc. Ang amo gini bala, Doc, how? Di ba,
Ah,
Doc, ang x kag y at pinch point ara pa ya sa 4 dapit sa 4. Ti
mhm.
kung kwaon mo lang intersection sang Q line, as ang equation ka Q line and the enriching section, makuha mo saya sa may dira, Doc, sa may tunga sa may feed tray dampi, Doc, nga point hindi ibala, Doc, ang sa number 4 sa fourth nga stage. Ti hindi ko sure, Doc, kung ano man dinagamuot ko.
Galing Josh, ini siya Josh ya. Ang nakabalo ko kabalo ko kung anong confusion mo. Kaya ang gina-after mo ang ini, ang after taya nga mabalaan taya si pinch point. Meaning ini siya yaho, say luhon mo ginadi siya Josh. Kay para lang makuha mo si pinch point. Kung makuha mo si pinch point, makasolve ka R sub m. Kay kinahanglan mo to siya sa graph. Hindi kay sili nga dapat ang scenario daw amo giniho. Ang kay ang aton nga condition sa minimum reflux ratio infinite number of stages. Infinite because tagkit anay ni sila nga tatlo dao ang curve ini si feed line kag si enriching section operating line sa dira nga point. So amo na nga kay wala man kita equation ni curve but kabalot nga ini silang tatlo makit-anay na sila ti alangan mga ang duha makit-anay di ini siya dire, meaning dira man na siya eh. So ang ila na lang ni intersection ni feed line kag ni enriching section operating line ang kwaon mo automatic na nga dira man na si curve. Kung diin sila nga duwa nagkitanay dira man na sa curve. So amo ni siya ang point nga hindi mo na ma-account, hindi ka naka-draw. You cannot anymore draw the stepping because nagdedla ka na di mo, hindi na siya ka-transfer kay Ari na di. Ang pinch point mo Ari gina di, hindi na siya kay ang namin mo ang iya nga intersection. Ari di, hindi di.
Hindi, Doc, bali bala, Doc, 'di ba ang equation of the enriching section amo gid ni siya, ang given nga formula amo ni siyang makuha mga line. Ti kung i-pinch point bala ay kung minimum, 'di ba, Doc, dapat masaka-saka ang line, makonektor siya sa babaw.
Mm.
Ti may lain naman, Doc, nga line pasaka sa babaw, Doc, ano man.
You mean ang slope sang imo enriching section
Oo,
operating line hindi na
yes, Doc. Hindi siya, Doc,
mag-similar?
magsaka sa babaw, Doc.
Wala ta galing gina-modify ang slope sang enriching section operating line.
Oo, Dok. Amo na ginaano ko, Dok, kay kung kwaon mo ang intersection sang Q line, ara sige sa tunga, hindi ya bala, Dok, ang sa may equilibrium curve.
Ang namin mo, ang makuha mo miss, wala na siya sa curve.
Oh, yes, miss. Tsaka ay amo na, Dok,
Mm.
ginamin ko, Dok.
Daw approximation, lagi na siya Diyos nga procedure. Kay wala man ta provided sa equation sang curve. Ang
Gani,
aton
Dok.
lang ginagamit, ang ginagamit ta lang nga premise nga kung diin sila magkit-anay nga tatlo, kaya dapat hindi man pwede nga si equilibrium curve lang kag si feed line lang ang mag-intersect nga si feed line niya at namin ko bala hindi man pwede nga sila dang di nga duwawo dason ari di siya sa dalom, so meaning dapat ini siya kag ini nakit-anay dang tatlo galing kay wala naman sang iban pang equation magamit, although na nag-get ko nang namin mo kay nga ang imo intersection miss amo ni siya ini siya amo ni hindi man na siya miss pinch point. Is that what you mean?
Yes, Dok. Sa
Oh,
bali, Dok, graphing lang gid daw, Dok, ang mas safe, Dok, eh.
pero ti hindi ka ka-graphing sa board. Amo na nga gina-approximate ta lang. Kay hindi man ka mag-graphing sa board exam. To wala man sang iban nga way nga unless naganya ka equations ang curve equilibrium curve, pero curve na siya. So take note, if it's curve, ang x squared, squared na, y squared na siya guro. Ano ni siya nga klase sa equation ni nga curve ni y in terms of x squared, si hindi lang may ara ka na da nga value sang x guro nga hindi mo pagpilion kay curve siya, hindi siya line. So dapat provide niya ka na. Kung wala ta other way of doing it.
Okay, Dok,
Mm.
Bali
O
amo na lang gagamiton, Dok.
nag-gets ko naman ang imo nga ginanami nga diri ni sila makitanay. Diri na sila makitanay. Galing wala na sang way pa. You can if you want, although tinaread ko naman atanan kay Jan ko please, amo gina siya ang procedure. Wala other way, though approximation siya isang graphical.
Okay, Dok,
Mm.
gi-clarify ko lang, Dok, kay na
Though hindi mo ma-reconcile,
oo, yes, Dok.
okay, do ari di siya. Ang iya naman na premise naging gamit nga ti makita na gid sila nga tatlo mo for pinch point, hindi pwede nga duwala ni. So ding assume na lang nga lapitanay na dio dire ang gwa ni pero tiyang iya sinislope malain gid ang imo nga reflux ratio malain siya. Pero amo na siyang procedure for now that you can use. Although sa una, mga estudyante ko, hindi pa na nila makita nga si Miss Ali, mag-graphical, gid nga pwede man lang i-diretso sa amo ni nga procedure. Ti mayo subong Diyos, kay nakita mo na nga ang graphical, mas naka-intindi ka pa nga, amo giniyang theoretical. Ang shortcut, ang term na shortcut nga procedure, gina-approximate yan lang. Kaya wala man siya sa equation yung magamit sa curve. So, approximation siya.
Gani, Dok. Sige, Dok.
Oh,
Thank you, Dok.
sige. May question pa? Although ikaw lang na naka-point out, Joshua, sa mga previous ko nga klase, why gid na why gid may nag think pag nga tuod, no? Approximation lang siya, kahit sa tunga-tunga na yung gingamit, hindi gid ang actual. And they would rather say nga mas mayo pa tani, diretso na lang, wala na lang graphical. But now the essence of the graphical, I think in this several minutes na nag-discuss sana, mas na-realize na guro sa mga classmates mo ninyo nga mas clear ang graphical kaysa sa approximation procedure lang. My question? Are there added questions? Point of clarifications? And we are on the 5th week na sa Monday, so we really are to finish distillation next week. That way, the remaining 4 weeks or 3 weeks, because the last week is the exam, will be for extraction. Extraction is a lot shorter than distillation in terms of the discussion. So, mas makaya siya sa 3 weeks. Unlike sa lawig-lawigid siya. Plus the fact that we also discussed in the first week the concept of phase equilibria with the orientation, and also we had a good 4 weeks also with distillation only. You have any question? No more questions for now? Sige ah. So, no more question for now. So, uh, that's it. Thank you for coming to class. How many are you now? 12. 12? Wait. Katrina, Ariana, Charmaine, Colleen, Arnica, Raymond. How come? What happened to the rest of the people? 11 of the 31, 32? Wait, class ha. One, two, three. Wait, class. Do you all have a copy? Wait, class, I have opened a different PowerPoint. Let me just share again. Part 2. Do you have a copy of John Couples? Of the 11 of you here, do you have a soft copy? Do you all have a soft copy of John Couples?
Yes,
Yes,
Guru.
miss.
Yes, miss.
Sinong wala?
Yes,
Sinong wala?
miss.
Sinong wala copy? May any chance? Sinong wala copy ni John Couples? Nan? Sige. So I've taken a screenshot of those who are present in class this afternoon. For your reading assignment, though I wrote it there in Canvas that this would be the reading assignment for this afternoon, I'd like you to do example 6, 11.6-2 of Jen Couples. When I say of do, all you have to do is read and understand and copy the solution of Jan Couples for this particular example and submit it through my email. Okay, it should not be submitted on Canvas because I know the students who are present right now. I like to write it as your seat for the day. Okay, this one, example 11.6, that's to pages 736 to 740 of Jan Couples. You have a good 1 hour and 40 minutes to do that. An hour, yeah, because we have one for it's not we still have more. You have more than an hour to do that. 30 minutes will be fine. That way I will have a seat work for those who are present in class this afternoon. Is that clear?
Hello,
For
Doc. Hello,
yes,
Doc. Ano ko di pala, Doc, sa school, Doc. Hindi ko dala ko dala din, Doc, mga gamit, Doc.
ara ka sa school. Oh my, wala ka dala nga gamit. Can you use data? Pwede ka send ko sa imo PDF copy sang book. I can send you PDF copy of the book.
Sige, Doc, try ko lang taon na kon. Pero lang taon ko dani, Doc, basi bala na save ko man din, Doc.
Jobern is also in school. Do you have a soft copy of the book, Jobern? Okay, sige. Para hindi na lang kapoy sa tanan, amo na lang ni. Wait, I'll read John Coop, Miss. Anyway, no, it's okay kasi si Joshua ato sa school, si Jobern ato sa school. Okay, this is what you're going to do now. I like you to write in 3 sentences for your seat work the 3 main things that you have learned in our discussion this afternoon. Submit it through my email. Don't submit in Canvas, but submit it to my email. Okay? Write in 3 sentences the 3 major learnings that you have learned this afternoon in our discussion. That way I can account that for seat work this afternoon. Is that clear, everyone?
Yeah. Yes, Doc.
There's
Yes.
12 of you here. Anyway, I know, okay, I took the screenshot of who are present. Submit through my email so that I will only have 12 submissions this afternoon for this particular requirement. Okay? And read the assignment. Read the assignment. I will give another sample problem on Monday with the same application of the topic that we have discussed this afternoon. Okay, we will discuss liquid extraction the week after next. Wednesday will be your preparation for your quiz on Thursday. Anyway, na-post ko naman gani sa Canvas. Wala ko lang gin-publish anay. You will have a quiz on your last quiz on Thursday for the topic 1 distillation. Okay? Do you have any question, class? You can just type, you can just compose in the email your 3 major learnings for the topic that we have discussed this afternoon, and that will be under sheet work for today's meeting. Is that clear? Any question? Okay, so there are no more questions. Let's call it a day. Thank you for coming to class. I hope you've learned something this afternoon. Bye for now.
Thank you, Miss.
Thank you,
Hey, Doc.
Miss.
Thank
Thank
you.
you,
Thank you,
Ma. Thank you.
Miss.
Thank you.